Imagine the most famous law in physics. Energy cannot be created or destroyed. Now imagine it has a hidden footnote. A footnote so important that, if you saw it, you would have to revise your entire understanding of how the universe works. The footnote was written in 1918 by a mathematician named Emmy Noether, and it has been sitting in plain sight for over 100 years. The footnote says this: energy is conserved when, and only when, the underlying laws of the universe do not change in time. If the rulebook is static, conservation holds. If the rulebook is moving, it does not. And our universe, expanding, accelerating, dark energy dominated, with a metric that is explicitly a function of time, is a universe whose rulebook is moving. The footnote applies. The conservation law fails at the cosmic scale. So when you ask the most natural question in the world, where does the universe find the energy to keep expanding? What does it feed on? The answer is stranger than the question. The largest accounting system in physics quietly stops working when you zoom out far enough, and almost nobody is told. Get comfortable. Hit subscribe if you have not yet. Because by the end of this, you will understand why dark energy can grow without a source, why the universe is not the closed system you were told it was, and why the question of what it feeds on has an answer nobody expects. Now, let us slowly settle into this. Part 1. The first lie. There is a sentence almost every person on this planet has heard at some point in their life. It sounds true because it has been repeated often enough, by enough teachers, that the brain has long since stopped checking it. The sentence is simple. Energy cannot be created or destroyed. It can only be changed from one form into another. A flashlight battery converts chemical energy into electrical energy into photons. A falling apple borrows from the gravitational potential energy of being held above the ground. A campfire releases the chemical bonds in dry wood and lets the energy flow into heat and motion. The bookkeeping is famous. The accounting is exquisite. The sentence is taught with the kind of confidence reserved for things people no longer feel the need to defend. You have almost certainly been told that sentence yourself. However it reached you the same way it reaches everyone: clean, unconditional, unqualified. Energy cannot be created or destroyed. Full stop. Move on to the next page. That sentence is, in the strict mathematical sense, not true for the universe that you actually live in. It is what physicists, in their quieter and more honest moments, call a lie to children. Not a malicious lie, not a careless one. A near truth, taught early to keep things simple, taught with the assumption that the student will eventually be told the rest, and then quietly, almost universally, never told the rest. The full statement is conditional. The full statement has a caveat that was left in a footnote, that was left out of the textbook, that was left out of the class. The full statement, the one a working cosmologist would defend without hesitation, the one that has been quietly governing the actual physics of the actual universe for over 100 years now, is this: energy is conserved in a system whose underlying structure does not change in time. You will notice that the sentence has an extra clause. You will notice that the extra clause was missing from every place you ever encountered the law before. And you will notice, if you sit with it for a moment, that the extra clause is doing all of the work. Get comfortable. You are about to walk through a piece of physics that almost nobody outside graduate school general relativity is ever taught, even though it has been settled science for over a century. The full statement of one of the most famous laws in physics has a hidden condition, and our universe does not satisfy that condition, and the consequences of that single fact ripple outward into the deepest open questions in modern cosmology. They explain why redshift drains energy from photons. They explain why dark energy can keep doubling without a source. They explain why physicists, when pressed, will admit that the universe does not have a well-defined total energy at all. And they explain why the question that this video is named after, where does the universe find the energy to keep expanding, was always, in a sense, the wrong question. But before any of that, let us start with the law as it is taught, because the law as it is taught is beautiful, and because seeing exactly what it claims and what it does not claim is the first step towards seeing why the universe does not have to obey it. The law as it is taught looks like this. Take any closed physical system. Inside it, energy can take many forms: kinetic, potential, thermal, chemical, nuclear, electromagnetic, rest mass. These forms shapeshift constantly, but the total, the law says, never changes. This is conservation of energy. In the form just described, it is one of the most useful, predictive, and experimentally confirmed statements in all of science. Every chemistry classroom uses it. Every engineering project ever has used it. Every nuclear reactor uses it. Every fusion experiment uses it. Every neutrino detector buried under a kilometer of rock uses it. The law works so well that physicists treat its violation as a sign something is wrong with the experiment, not with the law. When neutrinos were first proposed in 1930, they were proposed for exactly this reason. Beta decay seemed to be losing energy, and rather than admit energy was not conserved, Wolfgang Pauli postulated an invisible particle carrying it away. He was right. The neutrino was discovered 26 years later. The law held. The law always holds. Until you ask it a question, it was never built to answer. The question is this: what about the universe itself? Take all of it. Add up every battery, every photon, every star, every black hole, every cubic meter of empty space, every joule of dark energy, every gram of rest mass, every wisp of kinetic energy, in every gas cloud, in every galaxy, in every supercluster, across every cubic light year of the observable cosmos. Add up the gravitational potential energy of every pair of masses pulling on every other pair. Add it all up. Write the total down. Call it the energy of the universe. What does the law say about that number? The law, as it was taught to you in school, says the number is constant. The universe is a system. The system is closed. There is nothing outside it, by definition, because it is everything. Therefore, the total energy of the universe is conserved. That is what the simple version implies. And for most of human history, even most of the history of modern physics, that is what almost everyone assumed without thinking very hard about it. It is not true. And the reason it is not true is the most important caveat in classical physics, hidden inside a paper written by a German mathematician in 1918, sitting in plain sight ever since, quoted often by professionals and almost never mentioned to anyone else. The full version of conservation of energy is not unconditional. It is contingent on a property of the universe that our universe does not actually possess, and that single piece of information rewrites the whole question. There is no debt, there is no creditor. The universe is not finding the energy to keep expanding. It does not need to find any. The accounting law that would have forced it to find some does not apply to the kind of universe we live in. But to see why, you have to go back to a small room in Göttingen in 1918 and meet one of the most underappreciated mathematicians in the history of physics, who proved a theorem so deep that it rewrote what conservation laws even are. Her name was Emmy Noether. And the theorem she proved is the reason the rest of this video is going to make any sense at all. Part 2. The qualifier nobody mentioned. In 1918, in the small university town of Göttingen in Germany, a mathematician named Emmy Noether published a paper that almost no one outside of mathematical physics has heard of, and that almost everyone inside mathematical physics regards as one of the most beautiful theoretical results of the 20th century. The paper was titled Invariante Variations Problem, Invariant Variational Problems, and it appeared in the Proceedings of the Göttingen Academy of Sciences. The setting was modest. The result was not. What Noether proved, in the careful and unhurried prose of a mathematician working through a problem for the first time, was a theorem so general that it tied together two of the deepest concepts in all of physics. She proved that conservation laws and symmetries are the same thing. That sentence does not look impressive on a first reading, so let us slow down and unpack what it means. Because once you see what Noether actually proved, you will never look at conservation of energy the same way again. A symmetry, in physics, is a statement about something you can do to the universe that leaves the laws of physics unchanged. If you take all of your experiments and shift them 3 meters to the left, the laws of physics still work the same way. That is a spatial translation symmetry. The rules do not care where in space you do the experiment. If you take all of your experiments and rotate them 90 degrees, the laws still work the same way. That is a rotational symmetry. The rules do not care which direction your apparatus is pointing. If you take all of your experiments and run them tomorrow instead of today, the laws still work the same way. That is a time translation symmetry. The rules do not care when in time you do the experiment. Each of these symmetries is a statement of the form. The universe does not care about a particular kind of change. And what Noether proved in 1918 was that for every continuous symmetry of this kind, there is a corresponding conserved quantity. Every time the universe is indifferent to some kind of change, something gets conserved. The spatial translation symmetry, the fact that the laws of physics do not depend on where you are, implies the conservation of momentum. The rotational symmetry, the fact that the laws of physics do not depend on which way you are oriented, implies the conservation of angular momentum. And the time translation symmetry, the fact that the laws of physics do not depend on when you are, implies the conservation of energy. This is Noether's theorem. It is one of the deepest insights in mathematical physics, and it is the reason that conservation laws are not accidents. They are not arbitrary rules someone wrote down because the universe seemed to follow them. They are the direct mathematical consequence of the symmetries of physical law itself. When you see a conserved quantity in physics, you can always find a corresponding symmetry behind it. And when you see a symmetry, you can always find a corresponding conserved quantity behind it. Now, here is the part that almost nobody mentions. The theorem cuts both ways. If you have the symmetry, you get the conservation law. But if you do not have the symmetry, if the underlying structure of the universe does not have the property that the laws of physics are the same at every time, or every place, or every direction, then you do not get the conservation law. The conservation law fails. Not because anyone broke the rules, not because the universe is cheating. The conservation law fails because the symmetry it was built on top of was never there in the first place. This is the conditional that is missing from every textbook explanation of energy conservation most people ever encounter. The full statement is not energy cannot be created or destroyed. The full statement is energy cannot be created or destroyed in a system whose underlying physical laws do not change in time. Those two sentences sound similar. They are not the same. The first is unconditional. The second has a condition, and the difference between them is the difference between a law that holds always and a law that holds only when a particular property of the system is satisfied. The property is called time translation invariance. It is the technical name for the assumption that the rules of the universe do not change in time. If the metric of spacetime is the same now as it was a moment ago, and the same as it will be a moment from now, if the structural rules of how distances and durations work in your universe are not themselves a function of time, then time translation invariance holds, and Noether hands you conservation of energy as the corresponding conserved quantity. If the metric of spacetime is itself evolving, if the rulebook is being rewritten as the calendar pages turn, then time translation invariance does not hold, and Noether hands you nothing. There is no conservation law. There is no fixed total. The bookkeeping that worked when the structure was static stops working when the structure is in motion. You are about to learn that our universe is the second kind. Let us linger here for a moment, because this is the conceptual hinge that the rest of this video swings on. In the world of everyday human experience, time translation invariance feels like an obvious truth that nobody would think to question. If you do a chemistry experiment in your kitchen on a Tuesday, you expect the same chemistry experiment to give the same result on a Thursday. If you drop a rock from the same height under the same conditions, it falls in the same way every time. The laws of physics, on the kitchen counter scale, and the falling rock scale, and the laboratory bench scale, are extraordinarily consistent across time. To 20 decimal places, even the most exquisite atomic clocks running for years cannot detect any drift in the constants of nature. The fine structure constant, the speed of light, the masses of the elementary particles, all of these are constant in time within the precision of any experiment ever performed. So, at the human scale, and at the laboratory scale, and at the scale of the solar system, and even at the scale of the Milky Way, time translation invariance holds to staggering precision. Energy is conserved. The simple version of the law is correct. Every chemistry teacher who ever wrote energy in equals energy out on a chalkboard was correct in their domain. Every engineer who ever calculated the energy efficiency of a turbine was correct. Every biologist who ever traced the energy flow from sunlight to glucose to ATP to muscle motion was correct. The local conservation of energy is real. It is not a lie. It is one of the most powerful and useful laws we have. But there is a deeper level. There is a level at which the structure of space-time itself is in question. There is a level at which the metric, the mathematical object that defines what distance means, what duration means, how the geometry of the universe is put together, is not a fixed backdrop on which physics happens, but is itself one of the things that physics is doing. At that level, time translation invariance is no longer an obvious truth. It is a claim, and it is a claim that, in our universe, is false. Our universe is expanding. Not in the sense that there is some external void into which the galaxies are flying. Not in the sense that there is a place the universe is expanding into. The expansion is a property of the metric itself. The structural rules of how distances work in spacetime are themselves evolving as time passes. Every volume element you would integrate over to add up energy is itself a function of time. Every yardstick you would use to measure distance is itself a function of time. The rules of the box are changing as you try to count what is in the box. This is the situation Noether's theorem hands you nothing for. There is no time translation symmetry at the cosmic scale. There is no conserved quantity that you can identify as the total energy of the universe. The most famous law in classical physics has a missing premise, and our universe is exactly the kind of universe in which that premise is unsatisfied. Walk back through this, slowly, because the conclusion sits underneath everything else in this video. The simple version of conservation of energy holds in every laboratory, because every laboratory is a region of space-time that is, to extraordinary precision, time translation invariant. The rules in your chemistry classroom on Tuesday are indistinguishable from the rules in your chemistry classroom on Thursday. The rules in CERN's particle detectors during a Friday night collision are indistinguishable from the rules in CERN's particle detectors during a Monday morning collision. The constants of nature do not drift. The metric does not visibly evolve over the duration of any single experiment. So Noether hands you a conservation law, and the law works, and the books balance, and the engineers go home happy. But zoom out, step back from the laboratory, step back from the Earth, step back from the solar system, from the galaxy, from the local group, from the supercluster. Step back until you can see billions of light years at a glance. At that scale, the metric of space-time is doing something. It is stretching. It has been stretching for 13.8 billion years and shows no sign of stopping. The structural rules of how distances work are themselves on the clock. Time translation invariance. The assumption Noether's theorem requires before it will give you a conservation law is no longer satisfied. So you do not get a conservation law, not because someone took it away from you, but because the precondition for having it was never met. There is no global total energy of the universe. There is no fixed number that the cosmos preserves through its expansion. There is, at the largest scale, no ledger at all. A lie to children. The full statement was always conditional. The condition was never satisfied at the cosmic scale. And the universe has been running perfectly happily and perfectly consistently with general relativity without anything resembling a global conservation of energy for the entire 13.8 billion years of its existence. Now, you have to see what that looks like in practice. Because the abstract claim that energy is not conserved at cosmic scales is one thing, and the concrete examples of what that means for matter, for light, for gravity, and for dark energy are another. And once you walk through the four concrete cases, what happens when you stretch a box of mass, a box of photons, a box of two stars, a box of vacuum, you will see, in vivid detail, exactly how three different components of the same universe respond to the same expansion in three qualitatively different ways. None of them is wrong, none of them is cheating. They are simply each following the equation of state appropriate to what they are. And the total of all of them is not a constant. That is what this video is about. Let us start with the easiest case, the one that almost looks like conservation, the case of a box of mass. Part 3. The metric is the rules. Before we get to the box of mass, we have to put a name on the thing that is actually changing. Because if you want to follow what is going to happen to mass, to light, to gravity, and to dark energy as the universe expands, you have to understand what it means for the universe to expand. And the answer to that is going to be different from anything you were probably taught. When most people first hear that the universe is expanding, the picture they form in their mind is something like a fireworks display. The Big Bang is the initial explosion. The galaxies are pieces of debris flying through some pre-existing emptiness on their way to filling whatever empty room remains. That picture is wrong. It has been one of the most stubborn misconceptions in popular science for a century. The actual picture is stranger, and once you see it, the rest of this video falls into place. The galaxies are not moving through space. Space itself is stretching, and the galaxies are sitting still inside it. They are doing small motions of their own orbital motions, peculiar velocities, gravitational dances within their local clusters, but the overall recession of the galaxies from us is not motion at all. It is the metric of space-time, the structural rulebook that defines what distance means in our universe, doing something nothing in your kitchen, your laboratory, or your solar system ever does. It is changing in time. Let us linger on the word metric, because this word is the secret door into everything that follows. In ordinary geometry, the geometry you learnt in middle school distance is a fixed and obvious thing. If 2 points have certain coordinates, you compute the distance between them with a fixed formula, the Pythagorean theorem. The formula does not change from one moment to the next. The rules of how to compute distance are eternal and absolute. Geometry is a backdrop. Things happen against it. The backdrop itself never moves. In general relativity, that is not what geometry is. In general relativity, the geometry of spacetime is not a fixed backdrop. It is itself a physical thing with its own equations of motion, its own dynamics, its own response to the matter and energy distributed within it. Spacetime can curve. Spacetime can ripple. spacetime can expand. The metric, the mathematical object that tells you how to compute distances between nearby points and how to compute durations between nearby moments, is no longer eternal. It is no longer absolute. It is something that varies from place to place, and, in our universe, varies from time to time. In 1922, a Russian mathematician named Alexander Friedmann sat down with Einstein's field equations. The equations Einstein had published 7 years earlier as the heart of general relativity, and asked what the most general solution would look like for a universe filled, on average, with matter and radiation distributed roughly uniformly in every direction. The solution he found was startling. It described a universe that could not be static. The equations refused to allow a steady-state cosmos. They demanded that the metric itself be a function of time. Either the universe was expanding or it was contracting. It could not just sit there. Friedmann published his result in a German physics journal. Einstein initially dismissed it, then reluctantly accepted it after his own algebra checked out, and the field of physical cosmology was born. 5 years later, a Belgian priest named Georges Lemaitre, working independently and with rather more astronomical intuition than Friedmann had brought to bear, derived essentially the same result, and noticed that it implied a specific observational prediction. If the metric is expanding, then galaxies should appear to recede from us with velocities proportional to their distances. The farther away a galaxy is, the faster it should appear to be moving away. Lemaitre published this prediction in 1927 in a small Belgian journal in French, and it sank without much notice. 2 years after that, in 1929, the American astronomer Edwin Hubble published the observational confirmation: distant galaxies redshift in proportion to their distance. The universe is expanding. The metric is on the clock. The picture Friedmann derived from pure mathematics turned out to be the picture Hubble saw through his telescope at Mount Wilson. The metric Friedmann and Lemaitre wrote down, refined later by Howard Robertson and Arthur Walker, is now called the FLRW metric, after the four of them. It is the standard metric of modern cosmology. It is the structural rulebook of our universe at the largest scale. And it has, sitting right at its heart, a quantity that nobody can talk about cosmic expansion without mentioning. That quantity is called the scale factor. It is written as A and a small parenthetical t after it, indicating that it is explicitly a function of time. The scale factor, A of t. The scale factor is the thing that grows. At the beginning of the universe, it was extremely small. Today, it is much larger. Tomorrow, it will be larger still. And as the scale factor grows, every spatial distance in the cosmos grows proportionally with it. If two distant galaxies are 1 billion light-years apart today and A of t doubles, they will be 2 billion light-years apart, even though neither one of them moved through space at all. The spatial coordinates of the galaxies did not change. What changed was what the spatial coordinates mean. The metric reinterpreted the distances. Everything got farther apart not because anything travelled, but because the underlying rulebook redefined what far apart meant. Imagine, for a moment, a sheet of graph paper. On the paper, you have drawn a grid straight lines crossing at right angles, forming squares of identical size. Now place a few dots on the paper, at random grid intersections. These are your galaxies. Now slowly, while you watch, the paper itself starts to stretch. The grid lines remain at right angles. The dots remain at the same grid intersections they were assigned at the start, but the squares between them grow. What was a 1-inch grid becomes a 2-inch grid, then a 4-inch grid, then larger and larger still. The dots have not crawled across the page. They have stayed exactly where they were drawn, but every pair of dots is now farther apart from every other pair of dots than it was a moment ago. Not because anything moved, because the medium that defined what apart meant got bigger. That is what the FLRW metric is doing in our universe. The galaxies are dots on the cosmic graph paper. The metric is the paper. The metric is stretching. The galaxies are sitting still inside it. The recession we observe, the redshift we measure, is the signature of the paper expanding, not of the dots moving. Stay with this image because it makes the next move possible. If the metric is stretching, then any volume of space you define inside it is also stretching. If you draw an imaginary box around a region of intergalactic vacuum and let the corners of the box ride along with the cosmic graph paper, then the volume inside the box grows as the metric grows. This is what cosmologists call a co-moving volume, a volume whose boundaries are moving with the expansion of the universe, so that the same set of galaxies always sits inside the box, even as the box itself gets bigger. It is the natural volume for asking questions about how energy is distributed in an expanding universe, because the contents of the box are stable even as the size of the box is not. And now, finally, you have the setup you need. You have a metric whose scale factor is explicitly a function of time. You have comoving volumes that grow as the scale factor grows. You have a Noether theorem that requires time translation invariance to deliver conservation of energy. And you have a metric that is, by direct and unambiguous statement, time-dependent. The scale factor at time t is not equal to the scale factor at time t plus delta t. The structure of space-time now is different from the structure of space-time then. Time translation invariance is broken not by a small amount, not in some subtle technical sense, but in the most direct way possible, because the metric itself contains an explicit function of time, and that function is monotonically increasing. This is the formal statement of the situation. The FLRW metric has no time translation symmetry. Therefore, by Noether's theorem, there is no globally conserved energy. There is no number you can write down and call the total energy of the universe that the cosmos preserves through its expansion. The conservation law that you were taught as unconditional is conditional on a symmetry the universe does not have at its largest scale. Now let us slow down and feel where we are. Step inside a single comoving region of space. Imagine you can shrink yourself, mentally, to the size of a small sphere, a few megaparsecs across, far from any galaxy, somewhere in the intergalactic void. Hold still inside this sphere. Look around. The sphere is your co-moving box. Its boundary is defined by a handful of distant galaxies at the edges, all of which are co-moving with the expansion. Those galaxies will stay at the boundary as the universe expands. That is what co-moving means. But the volume inside the sphere is growing. The actual physical distance from one wall of your sphere to the opposite wall is increasing year by year, century by century, mega-year by mega-year. The volume element you would integrate over to add up energy is itself a function of time. The thing you are trying to count is being redefined while you count it. The grid is stretching under the integrand. The rulebook is being rewritten while you are still trying to read it. That image of standing inside a comoving sphere and watching the metrics silently stretch beneath you is what cosmologists carry around in their heads when they talk about expansion. The galaxies do not fly. The dots do not move. The paper grows. And every quantity you might try to integrate over the volume, every density, every count, every measurement of how much of something is contained inside a fixed comoving region is a quantity whose answer changes simply because the box is changing. Some quantities will scale down as the box grows. Some will scale up. Some will refuse to scale at all. Which quantity does what is determined by the equation of state of the substance in question? For dust, non-relativistic matter pressure is essentially zero, and the equation of state parameter W is zero. For radiation, pressure is 1/3 of energy density. W equals 1/3. For the cosmological constant, pressure is negative and equal in magnitude to energy density. W equals -1. Each substance responds differently to expansion of the metric. We are about to put 4 kinds of stuff inside our comoving sphere: mass, light, gravity, dark energy. Each will respond differently. None will conserve total energy the way you were taught. Start with the easiest case. Start with mass. Part 4. The mass case. Put a box of mass inside a co-moving region of space. Not a literal box made of cardboard, of course a conceptual box, a region whose boundaries are co-moving with the expansion of the universe. Inside the box, place some mass. It could be hydrogen atoms drifting in intergalactic space. It could be cold, dark matter slowly orbiting the gravitational potential of a halo. It could be any non-relativistic substance whose pressure is essentially zero compared with its rest mass energy density. The technical name physicists use for this kind of stuff is dust, even though it has nothing to do with the household variety. In the language of cosmology, dust is anything whose particles are moving slowly compared to the speed of light, so that the bulk of their energy is just the rest mass energy E equals mc squared rather than kinetic energy. Now ask the question, as the universe expands and the box grows, what happens to the total mass inside? The answer is the gentlest one you are going to see in this video, which is why we start here. The total mass inside the comoving box stays essentially constant. The box has gotten larger, but the same number of particles are inside it. None of them have left, because none of them are moving toward the boundary in any organized way. None of them have been added, because the box is closed in the co-moving sense, so the count of particles is the same. And since each particle has a rest mass that does not change as the box gets bigger, the rest mass of a hydrogen atom does not depend on the metric of spacetime, the total mass inside the box, in the sense of mass times the count of particles, is preserved as the box grows. In terms of density, this is the statement that the mass density scales as 1 over the volume of the box, which in turn scales as the cube of the scale factor. The mass density falls as a to the minus 3. If the scale factor doubles, the volume of the box increases by a factor of 8, and the mass density falls by a factor of 8. The mass density is 1/8 of what it was. But the total mass inside the box, the density multiplied by the volume, has stayed the same. Mass dilutes by the same factor that the volume grows by, so the product is unchanged. This is what conservation of mass looks like in an expanding universe. It is the closest thing to the law, as you were taught it, that you are going to see in this entire video. The total amount of dust inside a comoving volume is conserved across the expansion. The energy associated with that dust, which is just the rest mass energy mc squared summed over all of the particles, is also conserved. For non-relativistic matter, the simple version of energy conservation almost works. There is a footnote, even here, but it is small enough that we will leave it for later. The footnote is that the mass we are talking about is rest mass, and rest mass is what general relativity calls invariant mass. And invariant mass really is preserved under the kind of slow, smooth, large-scale expansion the FLRW metric describes. So for the matter content of the universe, in the simple counting sense, mass energy is conserved. The bookkeeping books balance. This is reassuring. This is the case that almost makes you think the simple version of conservation of energy might still hold. Because if matter does this, if matter dilutes in a way that exactly cancels the growth of the box, then maybe the whole universe behaves this way. Maybe all of the different forms of energy in the cosmos dilute in proportion to the volume, and the total energy of the universe is preserved through the expansion just on a per unit volume basis that gets thinned out as the universe gets bigger. It is a comforting thought. It is the thought a careful student might reach for in the middle of a cosmology class, having heard the bad news about Noether's theorem and the FLRW metric and looking for some way to rescue the simple law they were raised on. Maybe the law still works. Maybe it just works in the weak sense. Energy density times volume stays constant, so the total stays constant. Maybe the universe is, after all, a closed accounting system that preserves its books through the expansion, and the only thing that has changed is that we have to measure things in the right comoving units. Hold on to that thought. We are going to take it away from you in the next part. Because when we put light inside the box instead of mass, the comforting symmetry breaks. The dilution and the volume growth no longer cancel. The total starts changing. But before we get to light, there is a subtlety worth seeing. The reason mass energy is preserved in the naive sense under cosmological expansion is that the equation of state of dust is W equals 0. The pressure of cold, non-relativistic matter is negligible. When you put that equation of state into the continuity equation that governs how energy densities evolve under FLRW expansion, what falls out is that the energy density scales as 1 over the cube of the scale factor, and the total in any comoving volume stays constant. The continuity equation does almost all of the work in this video. In plain language, it says that the rate of change of the energy density is determined by the energy density itself, by the pressure, and by the expansion rate. Tell it the equation of state the W value, and it tells you exactly how the density scales with the scale factor. For dust, W is 0, density scales as a to the minus 3. For radiation, W is 1/3, density scales as a to the minus 4. For the cosmological constant, W is -1. Density does not scale at all. So the apparent miracle of mass conservation is not really a miracle. It is the consequence of the equation of state of dust being exactly the value that makes the dilution rate equal the volume growth rate. There is no symmetry behind this. It is just what falls out of the continuity equation when W is 0. The moment you put something with a different equation of state into the box, the apparent cancellation breaks and the total energy in the box changes. So, enjoy the mass case while it lasts, because the next case is light. And in the light case, the equation of state shifts to W equals 1/3, and the cancellation no longer holds, and the total energy in the co-moving box starts to fall. Not by a small amount, by many orders of magnitude over the history of the universe. The photons that warmed the early cosmos have lost most of their energy, not because anything stole it, not because anything absorbed it, not because they ran into a wall or a particle or a field that took the energy away. The energy is just gone. The comoving volume is bigger now than it was, and each photon inside it has less energy than it had before, and there is no counterparty, no debt, no creditor. The conservation law was always conditional, and the condition for radiation has never been met in the way it has been for matter. Let us walk into the light case. Bring your co-moving box with you. Empty it of mass. Fill it instead with photons. Then watch what happens when the metric does its work. Part 5. The light case. Empty the box of mass. Fill it instead with photons. A swarm of light, drifting between the co-moving walls, travelling at the speed of light in every direction, bouncing around with no preferred orientation. Each photon has a wavelength, and each wavelength is associated with an energy through one of the simplest and most famous relations in physics. The energy of a photon is Planck's constant times the photon's frequency, or, equivalently, Planck's constant times the speed of light divided by the photon's wavelength. Short wavelengths mean high energies. Long wavelengths mean low energies. A gamma-ray photon has an energy 1 billion times higher than a radio wave photon, simply because its wavelength is 1 billion times shorter. The same Planck-Einstein relation governs both. Now expand the box. The metric does its work. The scale factor A of t grows. And here, something happens that did not happen with mass. The photons inside the box do not just dilute by the increase in volume. Their wavelengths stretch. This is the redshift. This is one of the cleanest, most observed effects in all of modern astronomy. When the metric of space-time stretches, electromagnetic waves traveling through that metric stretch with it. A photon, emitted with a certain wavelength at an earlier epoch, arrives at us billions of years later with a longer wavelength than it had at emission. The amount of the stretch is precisely the ratio of the scale factor today to the scale factor at the time of emission. If the universe has doubled in size since the photon was emitted, the photon's wavelength has also doubled. The photon's frequency, which is inversely proportional to its wavelength, has halved, and the photon's energy, which is proportional to its frequency, has also halved. The photon has half the energy it had when it was emitted, not because it ran into anything, not because it transferred energy to a medium, not because of any interaction at all. The photon travelled in a perfectly straight line through perfectly empty space, and along the way, its wavelength got longer because the metric it was travelling through got longer. The energy decreased because the wavelength stretched. The wavelength stretched because the metric stretched. No counterparty was involved. No transaction occurred. The photon simply has less energy now than it had then, and there is no one and nothing that has the missing energy in its possession. Where did the energy go? That is the question that almost every undergraduate physics student asks the first time they encounter cosmological redshift, and it is a question that has a straightforward and slightly maddening answer. The energy did not go anywhere. It is not stored in some field. It is not transferred to some particle. It is not hiding in the gravitational potential of the expanding metric. It is just gone. The photon has lower energy than it had before, and there is no place in the universe where you can point and say, that is where the missing energy is. This is the first place in this video where the simple version of conservation of energy unambiguously fails. The mass case let you keep the comforting illusion that, even if total energy changes, total mass equivalent energy is preserved. The light case takes that illusion away. Photons inside a co-moving volume lose energy as the universe expands. The total electromagnetic energy inside the co-moving volume falls. The density falls faster than the volume grows. And if you do the integral, what falls out is that the radiation energy density scales as a to the minus 4, that is, 1 power of a steeper than the matter case. The volume grows as a cubed, the density falls as 1 over a to the 4th, and the total falls as 1 over a. The total radiation energy inside a comoving volume falls in direct proportion to how much the universe has expanded. This is not a small effect. This is one of the largest effects in cosmology. And in the early universe, when the scale factor was extraordinarily small compared to today, the total radiation energy in any comoving volume was extraordinarily large compared to what it is now. Let us put numbers on this. The cosmic microwave background, the radiation field that fills the entire observable universe today, as a uniform glow at a temperature of 2.7255 degrees Kelvin, is the same radiation field, in the co-moving sense, that filled the universe at the moment of recombination, about 380,000 years after the Big Bang. At recombination, the temperature of this radiation field was about 3,000 Kelvin. Today, it is just under 3 degrees Kelvin. The temperature has fallen by a factor of about 1100. The energy of each individual photon has fallen by the same factor, because for a thermal blackbody distribution, the temperature is directly proportional to the average photon energy. And the energy density of the radiation field has fallen by a factor of about 1100 to the 4th power, roughly 1.5 trillion. That is, the energy density of cosmic microwave background photons today is about 1.5 trillion times lower than the energy density of those same photons in the co-moving sense at recombination. If the universe were a closed accounting system that preserved total radiation energy, that factor of 1.5 trillion would have to show up somewhere. We would have to be able to point to where the missing energy went. We cannot. There is nowhere it went. The cosmic microwave background did not transfer its energy to matter. It did not transfer its energy to dark matter. It did not transfer its energy to dark energy. The energy did not leak out into another universe through some hidden channel. The energy is gone in the most literal sense. It is not stored anywhere. The total radiation energy in any comoving volume of the universe has fallen by 12 orders of magnitude since recombination, and there is no balancing entry on any ledger you can write down. Now go even earlier. Go back to the radiation-dominated epoch of the early universe, the first 50,000 years after the Big Bang, when the dominant component of the cosmic energy budget was radiation rather than matter. During this epoch, the universe was extraordinarily hot and dense. The scale factor was extraordinarily small, and the universe was expanding far, far faster than it does now. The total radiation energy in any co-moving volume was many orders of magnitude higher than it is today, perhaps 10 orders of magnitude higher, perhaps more, depending on exactly how far back you push the calculation and how careful you want to be about the neutrino contribution. Over the few 100,000 years, from the end of inflation to recombination, the radiation energy density inside any comoving volume of the universe fell by something like 10 orders of magnitude. 10 orders of magnitude, 10 powers of 10. That is the largest accounting error in the history of physics, if it were an accounting error. It is, depending on how you want to phrase it, either the largest discrepancy ever between the simple conservation law and the actual behavior of the universe, or it is exactly the behavior the FLRW metric predicts when you have a substance whose equation of state parameter is 1/3 and you put it through an early radiation-dominated expansion. Let us stand in this for a moment. The cosmic microwave background that bathes you right now is the same radiation, in the comoving sense, that was once thousands of times more energetic than it is today. Those photons, not metaphorically, those photons once carried so much energy per cubic meter that the entire universe glowed at the temperature of the surface of a star. And then the metric stretched, and the photons stretched with it, and the energy fell. Not because anything stole it, not because anything took it away. The energy simply was not conserved. That is the human stakes of the radiation case. The light that fills the universe right now is the surviving remnant of a vastly more energetic radiation field that has spent the entire history of the cosmos losing energy to nothing. Every photon in the cosmic microwave background today is a stretched-out version of a photon that was emitted at recombination with 1,000 times the energy. The energy did not go anywhere. It is just not there anymore. And the co-moving volume that contains those photons today contains, in total, about 10 orders of magnitude less radiation energy than the same co-moving volume contained when those photons were first liberated. You were not told this. You were told the law was unconditional. The law is conditional, and the radiation field is the first place where the condition shows its teeth. There is a stubborn intuition that wants to fight this conclusion. The intuition that energy must go somewhere, because energy always goes somewhere in laboratory physics. The intuition reaches for plausible counterparties. Maybe the energy went into the metric itself, like a balloon storing energy in its skin. Maybe into gravitational potential energy. Maybe into dark energy somehow. The intuition wants a transaction. The intuition wants somebody to be holding the missing energy. The mathematics does not provide one. The metric is not a balloon, and the work done in expanding it is not stored anywhere. Gravitational potential energy is not a well-defined quantity in the FLRW metric the way it would be in a Newtonian system. Dark energy has its own dynamics. Its density is constant for reasons that have nothing to do with the photons. There is no transaction. There is no counterparty. The photons lost energy because the metric expanded, and that is the whole story. The conservation law that would have demanded an accounting was conditional, and the condition is not met. This is the moment in the video where the floor starts to feel different under your feet. Up until now, we have been talking abstractly about Noether's theorem and metrics. Now we have a concrete number, 12 orders of magnitude, and the number names something real. The photons that warmed the early cosmos have lost most of their energy not because something stole it, but because nothing was making them keep it. The flat space-time intuition you have been carrying your whole life predicts that this should be a problem. The cosmological metric says no. The conservation law was always local. We still have to look at gravity, and we still have to look at dark energy. Let us turn to gravity now. Two masses that are not bound to each other and that ride along with the cosmic expansion grow farther apart over time. The gravitational potential energy of a pair of separated masses depends on their separation. As the separation grows, what happens to the potential energy? Part 6. The gravity case. Empty the box of photons. Replace them with two stars. Place the stars somewhere inside the co-moving box, separated by some distance. Each star has a mass. Each star is exerting a gravitational pull on the other. The two stars form a simple gravitational system, and that system has a property that anyone who has ever taken a freshman physics class can name. It has gravitational potential energy. Gravitational potential energy is one of the more notoriously slippery concepts in physics. Most people learn about it in the context of Earth's gravity. The higher you lift an object, the more gravitational potential energy it has, where more means a more positive number, and from which you can extract kinetic energy by letting the object fall. The energy of the lifted object is, in some bookkeeping sense, borrowed against the system that the lifter and the Earth and the object all collectively form. When the object falls, the borrowed potential energy is converted into kinetic energy and the books balance. In the case of two stars orbiting each other in deep space, the same kind of reasoning applies. The two-star system has a gravitational potential energy that depends on the separation between them. By the standard convention in physics, we take the 0 point of gravitational potential energy to be at infinite separation. Two masses that are infinitely far apart from each other have 0 gravitational potential energy. As they get closer, the potential energy becomes more negative. The closer they are, the more negative the potential energy. The pair has, in this language, a binding energy, a negative number that quantifies how tightly they are gravitationally bound. For two test masses separated by a distance r, the gravitational potential energy is minus g times m1 times m2, all divided by r. The minus sign is the key. The potential energy is always negative for two attracting masses, and it becomes less negative, that is, more positive, closer to 0 as the separation grows. Two stars far apart have a less negative gravitational potential energy than the same two stars close together. Now expand the universe. The metric stretches. The two stars are not gravitationally bound to each other in any tight orbital sense. They are sitting in the cosmic flow, and as the metric expands, they drift apart along with the expansion. Or, more precisely, if we treat them as co-moving objects, objects whose positions are defined by their location on the cosmic graph paper, rather than by any motion through space, then their physical separation grows as the scale factor grows. If A of t doubles, the distance between the two stars doubles. What happens to the gravitational potential energy? By the simple Newtonian calculation, the potential energy becomes less negative. The denominator r got bigger, so the magnitude of the potential energy got smaller, so the negative number that the potential energy represents is now closer to 0 than it was. The system has, in this bookkeeping, more total energy now than it did before. The kinetic energies of the two stars are essentially unchanged. Neither star is moving very fast relative to the local cosmic flow, so their kinetic energies are negligible. The rest masses of the two stars are unchanged. Stars do not lose mass just by being stretched apart by cosmic expansion. The total mechanical energy of the system is the sum of the kinetic energies, the rest mass energies, and the gravitational potential energy. The kinetic and rest mass terms have stayed the same. The potential energy has become less negative. The total has gone up. So in the gravity case, expansion gives you energy. The naive bookkeeping says that as the two stars drift apart along with the metric, the system gains energy because the binding energy that was holding them together has become a smaller magnitude negative number than it was. The total mechanical energy of the system is higher after the expansion than it was before. But, and this is where the case gets subtle, this analysis is doing something that general relativity refuses to let you do cleanly. It is treating gravitational potential energy as a well-defined number that can be assigned to a specific configuration of masses in a specific region of space. In Newtonian mechanics, you can do that. The gravitational potential energy of a pair of masses is a clean, frame-independent number that everyone agrees on. In general relativity, you cannot. There is no unique tensor that describes the energy of the gravitational field in general relativity. There are several competing definitions, each useful in some context, each ambiguous in others. They are called pseudo-tensors. They are not tensors. They depend on the coordinate system. Two different observers, using two different coordinate systems, can compute two different values for the gravitational potential energy of the same physical configuration, and there is no principled way to say which one is correct. This is a famously slippery point in general relativity, and it is one of the reasons that the total energy of the universe is not a well-defined concept. In Newtonian mechanics, gravitational potential energy is a clean concept, and total energy is well defined. In general relativity, gravitational potential energy is a coordinate-dependent quantity, and total energy is not generically well defined for an arbitrary spacetime. It is only well defined for certain special cases, like spacetimes that are asymptotically flat. An asymptotically flat spacetime is one that, sufficiently far from any mass or energy, looks like the flat Minkowski space of special relativity. The universe is not asymptotically flat. There is no sufficiently far away in the universe where the metric becomes Minkowski. The universe is everywhere expanding. The metric is everywhere FLRW, and there is no asymptotic region where the standard energy definitions of general relativity, the ADM mass, the Bondi mass, the Komar mass can be applied. So the simple Newtonian calculation that says two stars drifting apart in the cosmic flow have more energy than they had before is not quite right. It is using a Newtonian concept of potential energy that does not have a clean extension to the FLRW metric. The qualitative conclusion that the gravitational sector of the cosmic energy budget is doing something different from the matter sector and the radiation sector is correct. But the precise quantitative statement, the assignment of a specific energy to a specific configuration, is not. The gravitational potential energy of the universe as a whole is not a well-defined number. This matters, and we will return to it when we get to the zero-energy universe argument. For now, the qualitative point stands. In the gravity case, expansion of the metric changes the gravitational potential energy of any system of separated masses. For unbound masses riding the cosmic flow, the separation grows with the scale factor, and the gravitational potential energy becomes less negative. The system gains energy in the naive bookkeeping. For bound systems, galaxies, clusters, solar systems, the gravitational binding holds the system together against the cosmic expansion. Bound systems decouple from the Hubble flow. Their gravitational potential energy stays fixed. This is why the cosmic expansion does not pull apart the Earth-Sun system. The gravitational binding between the Earth and the Sun is enormously stronger than the tidal effect of cosmic expansion at the scale of the solar system. The orbital radius of the Earth is set by the dynamics of the Earth-Sun system, not by the FLRW scale factor. The Earth does not drift away from the Sun as the universe expands. Neither does the Milky Way drift apart from itself. Neither does the local group of galaxies that the Milky Way belongs to. All of these are gravitationally bound systems. Their internal structure is decoupled from the cosmic expansion, and their gravitational potential energy is essentially constant. The expansion shows up at scales above the level of bound structures. Two galaxies in different superclusters are typically not gravitationally bound to each other. The space between them is in the cosmic flow. The distance between them grows with the scale factor. The gravitational potential energy between them in the naive bookkeeping becomes less negative. The system, in the naive bookkeeping, gains energy as the universe expands. 3 different components, 3 different behaviors. The mass case looked like conservation because W equals 0 and dilution cancels volume growth. The light case showed energy loss because W equals 1/3 and dilution outpaces volume growth. The gravity case shows energy gain in the naive Newtonian bookkeeping because as unbound masses drift apart, the gravitational binding energy between them weakens, the negative number becomes closer to 0. The underlying reason for the divergence is not that anything strange is happening. Each component has a different equation of state, and each equation of state interacts with the expanding metric in a different way. There is no symmetry that requires the 3 to behave the same. There is no conservation law at the level of the total. The continuity equation handles each component separately, and the total of the 3 is not a constant. In one sentence, the universe contains stuff with different equations of state. The equations of state determine how each kind of stuff responds to expansion. The responses are different, and the sum total is not conserved, because the only thing that would have required it to be conserved time translation invariance of the metric does not hold. That is the whole story, in its mathematical bones. But we still have not gotten to the strangest case. We still have not gotten to the case where the dilution does not happen at all, where the density of a component of the cosmic energy budget is exactly the same before and after the expansion, regardless of how much the volume has grown. This is the case of dark energy. This is the case of the cosmological constant. This is the case that turned the whole question into a global mystery in the late 1990s and has been driving the field of cosmology for the better part of 3 decades. Stand inside your co-moving box, empty it of stars, empty it of photons, empty it of mass, and let nothing remain except the vacuum itself. Then watch what happens when the box doubles in size. Part 7. The dark energy case. Empty the box of stars, empty it of photons, empty it of dust and hydrogen and cold dark matter and every conventional component of the cosmic budget. Let the box contain nothing except the vacuum of intergalactic space, empty, dark, far from any galaxy, a region of the universe as close to truly empty as anywhere can be. There is still something in it. There is the cosmological constant, there is dark energy. There is, in modern cosmology, a constant background energy density that permeates all of space, every cubic meter of empty vacuum, anywhere in the universe, at a value of roughly 6 times 10 to the minus 10th joules per cubic meter. That number is tiny. In any human-scale region, it is negligible. The amount of dark energy in a cubic meter of vacuum is dwarfed by the energy of a single thrown baseball. The amount in a cubic kilometer is still small enough to be undetectable by any laboratory experiment yet devised. The reason cosmologists believe in it is not local. It is the global behavior of the universe, the way the expansion is accelerating in a way that requires a component with negative pressure That forces the value of about 6 times 10 to the minus 10th joules per cubic meter on us. This number is the energy density of empty space, of vacuum, of nothing. Now let the universe expand. The metric stretches. The co-moving box doubles in size. Watch what happens. The matter case, you remember, gave you density that fell as 1 over the cube of the scale factor. Volume up by 8, density down by 8, total unchanged. The radiation case gave you density that fell as 1 over the 4th power of the scale factor. Volume up by 8, density down by 16, total down by a factor of 2. The dark energy case gives you something neither of those does. The energy density of dark energy does not dilute with expansion. It does not fall at all. The vacuum of intergalactic space has the same dark energy density today, yesterday, 10 billion years ago, and 10 billion years from now. The density is constant. The scale factor changes, the volume changes, the matter density falls, the radiation density falls, and the dark energy density just sits there at 6 times 10 to the minus 10th joules per cubic meter, unchanging, indifferent to the expansion of the metric around it. What does this do to the total dark energy inside a co-moving box as the universe expands? The volume of the box doubles. The density of dark energy inside the box stays exactly the same. The total dark energy inside the box doubles. Stop and feel this. Read it again. The amount of dark energy in your co-moving box was X before the expansion. The box doubled in size. The density did not change. The amount of dark energy in your box is now 2x. Nothing flowed in from outside the box. Nothing was created by any quantum process inside the box. No nuclear reaction released the new energy. No conversion of one form of energy into another took place. The universe simply has more dark energy in this region now than it did a moment ago, because the region grew, and the density of dark energy did not respond to the growth by diluting the way matter and radiation do. This is not a conjecture. This is not a controversial position. This is the direct and uncontested consequence of dark energy having an equation of state parameter W equal to -1. The value that makes the continuity equation hand you a density that is constant under expansion. Plug W equals -1 into the equation, and what falls out is that the energy density is independent of the scale factor. Plug in any other value and you get some other dilution behavior. For exactly W equals -1, you get exactly no dilution. And the total energy inside any co-moving volume grows in direct proportion to the volume, which grows in direct proportion to a cubed. We have spent the last several parts of this video showing you components of the cosmic budget that respond to expansion in 3 different ways. Matter dilutes such that total in a co-moving box is constant. Radiation dilutes such that total in a co-moving box falls. Gravitational potential energy in the naive Newtonian bookkeeping behaves such that the system gains energy as separations grow. Now we add the 4th and strangest case. Dark energy does not dilute at all, and the total in a co-moving box grows, not by a small amount. The current universe is dark energy dominated. 68.3% of the cosmic energy budget today is dark energy, according to the Planck satellite's 2018 measurements. The dominant component of the cosmic energy budget is the component whose total in any co-moving volume grows with expansion. That means the total energy of the universe, summed over its components and integrated over a co-moving region, is currently increasing, exponentially increasing. Read that sentence one more time, slowly. The total energy of the universe is currently increasing exponentially with time, not because anyone is putting energy in, not because there is a source somewhere outside the universe pumping energy across the boundary, not because matter is being created from nothing in some quantum loophole. The total energy is increasing exponentially because the co-moving volume is increasing exponentially. That is what an accelerating expansion looks like, and the dark energy density that lives in every cubic meter of that co-moving volume is constant. Every new cubic meter of space that the expansion creates comes preloaded with the standard background dark energy density. There is no transaction, there is no source, there is no debt. The energy is simply there, in the new space, because the new space, like all space, has dark energy in it. Stand for a moment inside a cubic light year of intergalactic vacuum. The light year is a measure of distance, just over 9.5 trillion kilometers. A cubic light year is a region of space whose sides are each 1 light year long. Almost nothing is in your box. A few hydrogen atoms per cubic meter from the intergalactic medium, a few background photons from the cosmic microwave background, and the dark energy field at 6 times 10 to the minus 10th joules per cubic meter, summing to a total dark energy content of about 5.5 times 10 to the 45th joules across the whole cubic light year. Now wait a few billion years. The metric of space-time stretches around you. Your cubic light year co-moving, riding along with the expansion, becomes 2 cubic light years, then 4, then 8. The matter density falls. The photon density falls, and the photons individually redshift. But the dark energy density stays at 6 times 10 to the minus 10th joules per cubic meter, because the dark energy density does not depend on the scale factor. Each cubic meter of the new, larger volume has the same dark energy in it as each cubic meter of the original, smaller volume. The total dark energy in your co-moving box has doubled, then quadrupled, then octupled. There is no source, no inflow, no counterparty, no quantum process delivered the new joules. The universe simply has more energy now than it did a moment ago, because the metric grew and the dark energy did not dilute. This is the place where the question this video is named after starts to reframe itself in your head. Where does the universe find the energy to keep expanding? The question presupposes that the universe has to find energy somewhere, that there is a budget, that it has to balance, that there is an account being drawn down. The dark energy case shows the question is malformed from the inside out. The universe does not have to find energy anywhere because there is no conservation law at the cosmic scale that would require it to. The dark energy density is just a property of the vacuum. Every cubic meter of vacuum has it. When the volume grows, the total grows. No source needed, no transaction. There is no debt and there is no creditor. This is a complete change of the conceptual furniture. In the world you grew up in, energy was conserved. Every accounting question had an answer. In the world, the FLRW metric describes, at the cosmic scale, energy is not conserved. Some accounting questions have no answer because the global accounting framework does not exist, but it gets stranger. The dark energy density we observe 6 times 10 to the minus 10th joules per cubic meter is the number our two most powerful theories disagree about by a factor of 10 to the 120th power. The disagreement is the largest single mismatch between theory and observation in the history of science, and it sits underneath everything we have just talked about. If you are going to take seriously the question, where does the universe find the energy to keep expanding, you have to take seriously the parallel question, why does empty space have any energy density at all? And why is the value the universe actually observes so different from what our best theory of fields predicts? That is the cosmological constant problem, and it is the next part of this video. Part 8. The cosmological constant problem. In 1917, 2 years after he published the general theory of relativity, Albert Einstein sat down to apply his new field equations to the universe as a whole. He wanted a static cosmos. The prevailing astronomical wisdom of the time was that the universe was eternal and unchanging, and Einstein wanted his equations to give him a static solution. But when he plugged in a uniform distribution of matter and let the equations run, the solution refused to stay still. The matter, gravitating against itself, would cause the universe to collapse. To prevent this collapse, Einstein added a term to his equations. He called it the cosmological constant. He wrote it as a capital Greek letter lambda, and he chose its value precisely to balance the gravitational attraction of matter, holding the universe in a static, eternal configuration. 12 years later, Hubble published the observational evidence that the universe was expanding. The static configuration was an illusion. Einstein later called the introduction of the cosmological constant his greatest blunder. He thought he had added an arbitrary term to the equations to enforce a state of the universe that did not exist. He removed it from his theoretical framework. For most of the rest of the 20th century, the cosmological constant sat at zero in the equations of cosmology, a term that had once been needed for the wrong reason and was now happily set aside. Then, in 1998, two independent teams of astronomers published a finding that brought the cosmological constant back. Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt and Adam Ries's High-Z Supernova Search Team had been measuring the brightness of distant type Ia supernovae, exploding white dwarfs, whose intrinsic brightness is calibrated and known. By comparing their apparent brightness to their redshifts, the teams could measure how the expansion of the universe had been changing over time. The expectation was that the expansion would be decelerating, slowed by the gravitational pull of all the matter in the cosmos. What they found instead was that the expansion was accelerating. The universe was not just expanding, the expansion was speeding up over time. This required a component of the cosmic energy budget that exerted negative pressure, a component whose gravitational effect, in the language of general relativity, was repulsive rather than attractive. The cosmological constant, the term Einstein had introduced and then removed, did exactly this. With a positive value of lambda, the field equations of general relativity predicted an accelerating expansion of the kind the supernova data showed. The blunder was unblundered. The cosmological constant came back into modern cosmology, not as an arbitrary parameter chosen to enforce a static universe, but as the simplest available description of an observed accelerating expansion. Perlmutter, Schmidt, and Ries won the 2011 Nobel Prize in Physics for the discovery. In modern cosmology, the cosmological constant is interpreted as the energy density of the vacuum. It is dark energy in its simplest possible form. Every cubic meter of empty space, according to general relativity with a positive cosmological constant, has an intrinsic energy density that is the same everywhere and at every time. The value is set by the value of lambda, and from the supernova data and subsequent cosmic microwave background and baryon acoustic oscillation observations, that value is, to high precision, about 6 times 10 to the minus 10th joules per cubic meter. This is where the trouble starts. Quantum field theory, the framework that successfully describes the standard model of particle physics, that predicts the magnetic moment of the electron to 12 decimal places, that has been confirmed in thousands of experiments at high-energy accelerators, has its own opinion about the energy density of the vacuum. According to quantum field theory, the vacuum is not really empty. Even in a region of space with no particles, no matter, no radiation, the underlying quantum fields are still there, still fluctuating, still carrying zero-point energy. Every quantum field has a ground state energy, and the ground state energies of all the quantum fields combined contribute to the energy density of the vacuum. If you calculate this vacuum energy density by summing the zero-point energies of all the modes of all the standard quantum fields up to the Planck scale, the scale at which quantum gravitational effects are expected to become important, you get a number that is enormous. The result of the calculation, depending on exactly how you choose your cutoff, is something on the order of 10 to the 110th joules per cubic meter. That is a 1 followed by 110 zeros. The observed value of dark energy density is 6 times 10 to the minus 10th joules per cubic meter. That is the smallest number with a meaningful decimal in front of it that you can write down using the standard prefix system. The ratio of the predicted value to the observed value is 10 to the 120th power. That is 1 followed by 120 zeros. For comparison, the total number of atoms in your body is about 10 to the 28th. The total number of stars in the observable universe is about 10 to the 24th. The total number of subatomic particles in the visible universe is about 10 to the 80th. The mismatch between what quantum field theory predicts for the energy density of empty space and what cosmology measures it to be is 40 orders of magnitude larger than the number of subatomic particles in the entire visible universe. There is no comparable disagreement in the history of physics. The cosmological constant problem dwarfs every other open problem in fundamental physics by margins. The human mind has no apparatus for. Steven Weinberg, in his 1989 review article in the Reviews of Modern Physics, called it the largest discrepancy in all of physics. The phrase that has stuck is that the cosmological constant problem is the worst quantitative prediction in physics. Take a moment with this. Let the size of the discrepancy land. We have built telescopes, satellites, and cosmological surveys that work because dark energy has the value it does. We have published thousands of papers analyzing data from those instruments. The numbers all check out, internally, at the level of physical cosmology. The expansion rate, the temperature of the cosmic microwave background, the distribution of large-scale structure, all of it fits a model in which dark energy density is 6 times 10 to the minus 10th joules per cubic meter. The cosmological constant lambda is about 1.1 times 10 to the minus 52nd per square meter, and the universe has been gradually transitioning from radiation-dominated to matter-dominated to dark energy-dominated over the past 13.8 billion years. The mathematics works. The observations confirm the picture, and underneath it, our best theory of the very small says that the dark energy density should be 10 to the 120th times larger than the value the universe actually has. Either quantum field theory is wrong in a way that has not yet been caught, despite being one of the best tested theories in science, or general relativity is wrong about how vacuum energy gravitates, or some delicate cancellation is taking place that brings 10 to the 110th almost exactly down to 10 to the minus 10th, leaving only the residual we observe. Nobody knows which. This is the deepest open problem in modern physics. It drives the interest in quintessence, where dark energy is a dynamical scalar field whose value can evolve. It drives the interest in modified gravity, where the accelerating expansion comes from a modification of Einstein's equations rather than a vacuum energy term. It drives the interest in the holographic principle, where the energy density of empty space is constrained by the entropy of the cosmological horizon, rather than by zero-point energies of local quantum fields. More than any other problem, it suggests our current theoretical framework for talking about energy in the cosmos is incomplete. The largest single mistake in all of human science is the difference between what quantum field theory says the energy of empty space should be and what cosmology measures it to be, 120 orders of magnitude. The number written out is a 1 followed by 120 zeros. More zeros than there are atoms in your body. More zeros than there are subatomic particles in the visible universe by a factor of 40 orders of magnitude. Two of the most successful frameworks humans have ever built disagree about the energy of empty space by a factor that has no analogue in any other branch of science. And we have built telescopes, satellites, and cosmological surveys on the smaller number, because the smaller number is what the universe actually does. Nobody knows why. This is not a small open problem. It is the largest open problem. The cosmological constant problem matters for the larger question this video is asking, because it shows you that, even within the framework where dark energy is the explanation for the accelerating expansion, we do not actually understand the energy of empty space. We have measured its value to good precision. We have no idea why it has the value it has. Whatever dark energy is, whatever process or principle or accident sets its density to the number we observe, that process is operating outside of our current theoretical understanding. The question, where does the universe find the energy to keep expanding, is one face of a deeper question: what is the structure of the vacuum? What fields and quantum effects contribute to its energy density? And why does the result land on a value that is precisely tuned to allow the universe we see? We do not know. After more than 100 years of general relativity, after 80 years of quantum field theory, after a Nobel Prize for the discovery of accelerating expansion, after 30 years of intense theoretical and observational work on dark energy, we still do not know. The accounting framework we have is incomplete. The continuity equation tells us how dark energy density behaves under expansion. It does not tell us why the density has the value it does. The simple version of conservation of energy was wrong because the FLRW metric does not satisfy time translation symmetry. The next layer down, the question of where the dark energy density itself comes from and why it has its specific value, is wrong because we do not know what dark energy is. And in the next part of this video, we are going to consider one of the most popular attempts to rescue some form of energy conservation at the cosmic scale, the zero-energy universe argument, the idea that the total energy of the universe is exactly zero because the positive mass energy is exactly cancelled by the negative gravitational potential energy. This is a famous argument. It shows up in Hawking's books, in Krauss's books, in pop science talks all over the internet. It is presented as evidence that the universe can come from nothing without violating any conservation law, because the total it would have to come from is zero. It is a beautiful argument, and it has a subtle catch that almost nobody mentions, and we are about to walk through both halves of it. Get ready, the zero-energy universe is next. Part 9. The zero-energy universe argument and caveat. In 1973, a physicist named Edward Tryon published a short paper in the journal Nature with the provocative title, "Is the Universe a Vacuum Fluctuation?" The paper made an audacious suggestion. It proposed that the entire universe, every star, every galaxy, every photon, every joule of mass energy could be the result of a quantum fluctuation in some pre-existing vacuum state. The argument depended on a specific accounting claim. The total energy of the universe, Tryon argued, was exactly zero. The positive contribution from all of the mass energy and radiation energy and dark energy in the cosmos was, in his calculation, precisely cancelled by the negative contribution from the gravitational potential energy of all the matter pulling on all the matter. The two giant numbers summed to zero. And because the total was zero, the universe could come from nothing without violating any conservation law. This argument has had a long and influential life. Stephen Hawking developed similar ideas in his 1988 book, A Brief History of Time. Lawrence Krauss extended them in his 2012 book, A Universe from Nothing. Both books are popular enough that the zero-energy universe argument has become, for many people, the standard answer to the question of how energy conservation can be reconciled with cosmic expansion. The story has a satisfying tidiness to it. The universe is a system. The system has total energy 0. Energy is conserved at the value 0. The universe can come into being from nothing without breaking any law. The blackboard is wiped clean. Everything balances. Let us walk through the argument in detail, because it is worth seeing in its full form before we look at the catch. The positive side of the ledger is straightforward. Add up all of the mass energy in the observable universe. The visible matter, stars, gas, dust, comes to about 5% of the cosmic energy budget, which for the observable universe works out to something on the order of 10 to the 72nd joules. Add in dark matter at about 27% of the budget. Add in dark energy at about 68%. Add in the small contribution from the cosmic microwave background and other forms of radiation. Total: somewhere on the order of 10 to the 72nd joules of positive energy in the observable universe, dominated by dark energy in the modern era, dominated by matter and dark matter in the recent past, dominated by radiation in the early universe. The negative side of the ledger is the gravitational potential energy. Every mass in the universe is gravitating on every other mass. Every pair of masses, by the standard Newtonian bookkeeping, has a negative gravitational potential energy proportional to minus g times the product of the two masses divided by their separation. Sum this up over every pair of masses in the universe, and you get a negative number that is, in the standard calculation, of approximately the same order of magnitude as the positive total, 10 to the 72nd joules, more or less, of negative gravitational potential energy. The two numbers cancel. The total comes out to approximately 0, and the argument concludes. The total energy of the universe is 0. The universe can come into being from nothing without violating energy conservation, and therefore, the original creation of the universe is consistent with the law of conservation of energy at the cosmic scale. It is a beautiful argument. It is intellectually satisfying. It rescues the simple version of the law without requiring us to confront the Noether conditional. It says that energy is conserved at the value 0, that the universe started with 0 total energy and has 0 total energy now, and that all the expansion and all the cosmic evolution we observe is just a redistribution of energy between positive and negative contributions whose sum is always 0. The accounting books balance just at the value of 0 rather than at some non-zero total. There is just one problem. The calculation depends on assigning a specific number to the gravitational potential energy of the universe. And in general relativity, that number does not have a unique definition. This is the catch that almost nobody mentions. The gravitational field of general relativity does not have a localizable energy density the way the electromagnetic field does. There is no clean, frame-independent way to write down the gravitational potential energy density at this point in spacetime and have all observers agree. What you can write down instead is a pseudotensor, a mathematical object that transforms differently under coordinate changes so that different observers, using different coordinate systems, compute different values for the same physical configuration. There are several competing pseudotensors in the general relativity literature: Einstein's own, Landau, Lifshitz, Müller, Bergman, Thomson, Weinberg. These are all different mathematical objects, each yielding different numerical values for the same physical configuration. None is obviously correct. When the zero-energy universe calculation is performed, the result depends on which pseudotensor you choose. In some choices, the answer comes out to exactly 0. In others, it does not. The 0 of the zero-energy universe is not a unique, observer-independent 0. It is contingent on a bookkeeping choice the calculator makes, often without remarking that they have made it. This is the fundamental reason the total energy of the universe is not a well-defined concept in general relativity. The standard machinery provides several candidate definitions, each giving a different answer for a non-asymptotically flat spacetime. The FLRW metric is not asymptotically flat. There is no preferred frame in which to compute the energy of the universe. Energy is, in the deep sense, not a well-defined cosmic quantity. So the zero energy argument is not wrong. It is one of several possible answers. It is the answer you get when you choose certain coordinate systems and certain pseudo-tensor definitions. It is a legitimate result in a particular bookkeeping framework, but it is not the unique or canonical answer because there is no unique or canonical answer to find. This subtlety is not always mentioned in popular presentations. Hawking's treatment in A Brief History of Time is careful in some places and loose in others. Krauss's treatment in A Universe from Nothing is more emphatic about the zero and less explicit about the pseudo-tensor dependence. The argument has been criticized. David Albert wrote a famously scathing review of Krauss's book in the New York Times, pointing out that the nothing of A Universe from Nothing is actually a quantum field in a particular state, which is not really nothing at all. What does this mean for how to think about the zero-energy universe argument? It does not mean the argument is wrong. It is a real and interesting calculation that, in certain natural coordinate systems and certain natural pseudo-tensor choices, gives an answer of exactly zero for the total energy of the universe. That is meaningful. It tells you something about the structure of the cosmos, that a non-trivial cancellation between positive mass energy and negative gravitational potential energy occurs to high precision in standard bookkeeping. That is not nothing. What it means is that the argument should not be presented and should not be heard as a unique and definitive resolution of the energy conservation problem at cosmic scales. The zero is a contingent zero. It depends on choices. A different choice gives a different answer. And the deeper resolution of the energy conservation problem at cosmic scales, the one that all serious modern cosmologists adopt, is not to say the total energy is zero. It is to say the total energy of the universe is not a well-defined quantity because the symmetry that would have made it well-defined does not hold. And asking the question presupposes a framework that does not apply here. This is what Sean Carroll, the physicist who has perhaps done the most public work over the last decade and a half to clarify the energy non-conservation in cosmic expansion, has consistently emphasized. The question, where does the energy come from, presupposes a conservation law. The conservation law does not hold in the FLRW metric. The question is malformed. The dark energy density does not need to come from anywhere, because there is no rule that says it has to. The zero-energy universe argument is interesting as a piece of bookkeeping in particular coordinate systems, but should not be taken as the definitive answer, because there is no definitive answer to find. The whole question rests on a premise that the metric of our universe does not enforce. So we have, by the end of this part, 3 positions a working cosmologist could hold. The first is the malformed question position Sean Carroll's. The question's premise is wrong. There is no conservation law at the cosmic scale, so there is nowhere for the energy to come from. The expansion is just what the metric does. The second is the zero-energy universe position, Tryon, Hawking, Krauss. The total is exactly zero. Positive mass energy and negative gravitational potential energy cancel. The catch is that the zero depends on the pseudo-tensor choice. The third is the unanswered question position. We do not actually understand what dark energy is. The cosmological constant problem is open. QFT and GR disagree by 120 orders of magnitude. The honest answer is that we are not sure. These are not 3 different opinions about the same fact. They are 3 different interpretations of what the fact even is. In the next part, we walk through each in more depth. Part 10. 3 honest positions. There are roughly 3 honest positions a working physicist can hold on where does the universe find the energy to keep expanding. We have already named them in the last part. Now we want to walk each one of them through to its end, because they are not just 3 different ways of saying the same thing. They are 3 different ways of being in the universe, 3 different temperaments of relationship with the open question, 3 different things to hold in your mind when you next encounter someone confidently asserting one or another of them. The first position is the malformed question position. It is most clearly associated with Sean Carroll, the cosmologist and writer who has spent a remarkable amount of public-facing time making this single point about conservation of energy. His view, repeated in essays, in public lectures, in podcast appearances, in his book The Big Picture, and most pointedly in a famous Discover magazine blog post titled simply, "Energy is not conserved," is that the question this video is named after has a hidden premise that does not survive scrutiny. The premise is that there is, somewhere, a conserved quantity called the total energy of the universe, and that any change in the cosmic budget must be reconciled against that conserved total. The premise is false. There is no such conserved quantity. There is no such total. The Noether theorem requires time translation symmetry to deliver conservation of energy. The FLRW metric does not have time translation symmetry, and therefore there is no globally conserved energy at the cosmic scale. The end. The question is malformed because the framework it presupposes does not apply. In this view, the expansion of the universe does not require any energy source. The dark energy density does not come from anywhere. The cosmological constant is just a constant background energy density of the vacuum, and as the co-moving volume grows, the total dark energy in that volume grows in lockstep with no need for any process to add energy from outside. The accelerating expansion is exactly what the equations predict for a metric with a positive cosmological constant. The mystery is not a mystery. The mystery is an artifact of bringing flat spacetime intuitions to a curved spacetime problem and being surprised when the intuitions do not apply. The strength of this position is that it is technically airtight. Carroll is not making a controversial claim. He is reading out, in plain language, what general relativity actually says about its own mathematical structure. The energy non-conservation in the FLRW metric is a textbook result. Every working cosmologist knows it. What Carroll has done is just say it out loud, repeatedly, in places where people who do not work in cosmology might hear it. The position has the texture of a deflation. It does not solve the puzzle so much as dissolve it. The puzzle was an illusion all along. The question vanishes when its hidden premise is named and discarded. The weakness of this position is that it leaves some people unsatisfied because it does not provide a positive story. It does not tell you what dark energy is. It does not explain why the cosmological constant has the value it has. It does not address the cosmological constant problem at all. It simply notes that, even before you get to those deeper questions, the surface question of where does the energy come from was malformed and does not need an answer. Some physicists, and many non-physicists, want more than that. They want a story about where the energy comes from, even if the answer is that it comes from a property of the vacuum that we do not yet understand. The malformed question position does not give them that story. It gives them a clearing away of a confusion, which is intellectually valuable but emotionally less satisfying than a positive narrative. The second position is the zero-energy universe position, associated with Edward Tryon, Stephen Hawking, and Lawrence Krauss. In this view, energy conservation is rescued at the cosmic scale by the observation that the total energy of the universe is, in standard bookkeeping, exactly zero. The positive mass energy of all matter and radiation and dark energy is cancelled by the negative gravitational potential energy. The total is zero. Energy is conserved at the value 0. All cosmic evolution is just a redistribution between positive and negative columns of a ledger whose row total is always zero. The strength of this position is that it preserves a structure many people find comforting. There is still a conservation law. The puzzle of energy coming from nowhere is resolved by saying the net is always zero. The argument also has the virtue of being a real and interesting calculation. The cancellation is what falls out of the standard machinery when you apply it to a cosmologically realistic configuration. The weakness, as we walk through in the previous part, is that the zero is contingent on the choice of pseudo-tensor. There is no unique definition. Different choices give different numerical answers. The argument is meaningful with the caveat. Strip the caveat away and it becomes overstated. Many physicists are sympathetic to the argument in spirit, while uneasy about its frequent presentation without the caveat. The third position is the unanswered question position. Both of the first two are partial. The malformed question position is right that the FLRW metric has no globally conserved energy. The zero energy argument is right that there is an interesting bookkeeping calculation that gives zero in standard frames. But neither addresses the deeper problem we do not understand what dark energy is, why it has the value it does, or how to reconcile the QFT prediction with cosmological observation. The cosmological constant problem is not resolved by either of the first two positions. In this view, the question sits inside a larger, open problem we do not yet have the physics to address. The working description has gaps. The gap at the heart of the dark energy puzzle is 120 orders of magnitude wide. We do not know if the right resolution will come from quantum gravity, holography, emergent spacetime, modified gravity, or something nobody has yet thought of. We are honest about not knowing. The strength of this position is its honesty. It does not claim more than the evidence supports. The weakness is that it offers no satisfying resolution. It leaves the listener exactly where they came in, with an open question, no answer, just the additional context that the question is hard and that working physicists do not have a consensus answer either. Most working cosmologists hold some combination of all three positions, depending on the subfield they work in and the specific question they are being asked at the moment. A cosmologist who works on the formal structure of general relativity will likely give you the malformed question position, the Noether theorem is clear, the FLRW metric is clear, the non-conservation is clear. No deeper mystery at the level of classical GR. A cosmologist who works on the early universe may give you the zero energy position because the question of whether the universe could have come from nothing is live in that subfield. A cosmologist who works on dark energy phenomenology will give you the unanswered question position because they know there is still a number 6 times 10 to the minus 10th joules per cubic meter that nobody can derive from first principles. So the answer is not a single answer. It is 3 answers, none of which is wrong, all of which are partial, and the choice between them is more a matter of which face of the question you are looking at than a matter of who has the right interpretation. This is what serious modern cosmology looks like from the inside. Not one clean answer, but a layered set of partial answers. The universe is a more complicated and more interesting place than the simple law of conservation of energy was ever going to capture. In the next part, we come back to the simple law one more time, because there is one part of it that survives all of this, the local conservation of energy. The version of the law that works in your laboratory, in your body, in every chemical reaction, in every cell, in every particle collision, in every nuclear decay, that version is real. That version is unbroken. That version is what survives. Walk into the next part. The law was never wrong. It was just smaller than you were told. Part 11. The local conservation that survives. There is one more piece of the story that has to be told, because without it the picture is incomplete in a way that misleads. We have spent the last several parts of this video walking through the ways in which the simple, unconditional version of the law of conservation of energy fails at the cosmic scale. Mass dilutes in proportion to volume. Radiation dilutes faster than volume grows, losing energy as the metric stretches. Gravity does something subtle and coordinate-dependent. Dark energy does not dilute at all, and its total in any comoving volume grows with the expansion. The continuity equation governs all of this. Noether's theorem explains why there is no global conserved quantity to play the role of total energy of the universe. The malformed question position dissolves the puzzle. The zero-energy universe position offers a contingent zero. The unanswered question position points to the cosmological constant problem and admits that we do not yet have the framework. All of this might leave a listener thinking that conservation of energy is broken in a deep sense, that the law was wrong, that it has been a mistake all along, that physics never had a real conservation law for energy, that the equations of general relativity have no respect for this kind of bookkeeping. That is not what is going on, and the difference matters. Energy is conserved in our universe. It is conserved everywhere, at every point, at every instant. The conservation is real and it is everywhere. What fails is the act of adding up the conservation at every point into a single global statement. This is the most important distinction in the entire video. Local conservation is exactly preserved by the equations of general relativity. Global conservation is not. The two are different statements, and they are both true at the same time. The mathematical statement of local conservation in general relativity is something called the Bianchi identities. In the language of tensor calculus, the Einstein field equations say that the curvature of spacetime, encoded in a quantity called the Einstein tensor, is proportional to the energy-momentum content of spacetime, encoded in a quantity called the stress-energy tensor. The Bianchi identities are a set of mathematical identities that the Einstein tensor automatically satisfies by virtue of the geometric structure of how the field equations are constructed. The Bianchi identities, applied to the field equations, give you a statement called the covariant conservation of stress energy. In symbols, the covariant divergence of the stress-energy tensor is zero everywhere, at every point in spacetime, regardless of what coordinate system you use or what metric you have. The covariant conservation of stress energy is the precise mathematical statement that energy is locally conserved everywhere in the universe. It says, at every point in spacetime, the rate at which energy is flowing into a small region is exactly equal to the rate at which energy is leaving that region, plus or minus any local sources or sinks. In ordinary physics language, energy and momentum are conserved at every point in the same way they would be in flat spacetime, with the additional subtlety that conserved in curved spacetime means something slightly more nuanced than the naive Newtonian version. Every chemical reaction in every laboratory on Earth conserves energy. The covariant conservation of stress energy guarantees it. Every particle collision at the Large Hadron Collider conserves energy. Every neutrino interaction inside a kiloton of liquid argon in a deep underground detector conserves energy. At the laboratory scale, the metric is, to extraordinary precision, flat. Time translation invariance holds locally. Noether's theorem hands back conservation of energy. The bookkeeping works everywhere the metric is approximately stationary, everywhere small enough not to feel the cosmic expansion. This is most of where you and I live. Our entire experience of the physical world, every observation, every chemical reaction in our bloodstream, every photon emitted by every star whose light reaches our retinas, all of it takes place in regions of space-time that are, to extraordinary precision, locally time translation invariant. Energy is conserved exactly to within the precision of any measurement ever made, anywhere physics is actually done. When a chemistry teacher tells you energy is conserved in a chemical reaction, they are telling you the truth. They are stating a law that holds with exquisite precision in the regime they are describing. The local conservation of energy is one of the most robust and useful laws in all of science. It is not weakened by the fact that global conservation fails at the cosmic scale. The two are different statements, and the local one is, in its proper domain, unbreakable. What changes at the cosmic scale is just one thing. You cannot sum the local conservation up into a single global statement about the total energy of the universe. The summation requires time translation invariance over the entire spacetime, and the FLRW metric does not have that. So the integral over all space of the energy density does not give you a quantity that is independent of time. The local rate of change of energy at each point is determined by the local pressure and the local expansion rate through the continuity equation. The sum of all those local rates of change is not zero. It is whatever the integrals work out to be, given the equations of state of the various components of the cosmic budget. For matter, the integrated total stays constant. For radiation, it decreases. For dark energy, it grows. The local conservation is satisfied at every point energy is not being created or destroyed locally. But the local rates of change do not sum to zero because the metric is not stationary. This is the resolution that the cosmological constant problem and the cosmic energy question and the dark energy mystery have all been pointing at. The law of conservation of energy is real. It is exactly conserved at every point in spacetime, including every point in your laboratory, every point in your body, every point in every star, every point everywhere. The Bianchi identities of general relativity guarantee it. What was always implicit, and what was almost never said out loud in introductory textbooks, was that the local conservation does not automatically extend to a global one. The extension requires a symmetry that the expanding universe does not have, so the local law stays. The global law was always conditional, and the condition is not satisfied at the cosmic scale. In one sentence, energy is conserved in every part of the universe, and not in the universe as a whole. That sentence sounds like a paradox. It is not a paradox. It is a precise statement of what general relativity says, and once you understand the conditional version of Noether's theorem, it is exactly the structure you would expect. The local time translation invariance, true at every point to extraordinary precision in any region, small enough not to feel the cosmic expansion, gives you the local conservation law, point by point. The global lack of time translation invariance true at the cosmic scale, because the scale factor is a function of time, denies you the global conservation law. Both statements are simultaneously true. They are not in conflict. They are simply addressing different scales. This is what working physicists understand, and what most non-physicists are never told. The cleanest way to put it might be this. The simple version of the law of conservation of energy, as taught in introductory textbooks, is true everywhere that the metric of spacetime is approximately stationary. It is true in your kitchen, in your laboratory, in your body, in any chemical reaction, in any nuclear reaction, in any solar system, in any galaxy, in any region small enough that the cosmic expansion does not produce a measurable effect within the region. It is true everywhere you live. It is true everywhere you will ever observe. It is only when you try to extend the law to cover the entire cosmos, including the time-evolving metric of the FLRW background, that the law as a global statement fails. And the failure is not a defect, it is the signature of a universe whose metric evolves. This is the resolution. The law was not wrong. It was just smaller than the listener was told. At every point in the listener's body, in every chemical reaction in their bloodstream, in every electron jumping in every atom, energy is conserved exactly. The Bianchi identities of general relativity guarantee it. The mistake was the leap from true at every point to true when added up over the entire universe. That leap is what fails. And the failure is not a defect, it is the signature of a universe whose metric evolves. The listener leaves the chapter with the law intact and the cosmic accounting reframed. This is what we have been building toward. The conservation law you learned was real, and it is intact, and it is one of the most precisely confirmed laws in all of science. What was missing from the textbook was the qualifier. The qualifier names the domain in which the law holds. The domain is everywhere that time translation invariance is satisfied. That is, in our universe, every local region. The qualifier excludes the cosmic scale, where time translation invariance is not satisfied. And outside the domain, the law as a global statement does not apply. There is one part left to this video, the closing reframe, walking the listener out of the deep technical material and back into the world they came in with the question they came in with held lightly and reframed gently. The universe is not finding the energy to keep expanding. There was never any energy to find. The question carried a hidden premise that the listener was taught without knowing it. Once the premise is named and let go, the mystery doesn't disappear, it shifts. The new mystery is not, where does the energy come from, but what kind of universe is the kind where the most famous law in physics is conditional? Let us walk into that closing reframe. Part 12. The closing reframe. So, where does the universe find the energy to keep expanding? We can answer it now. After 11 parts of walking carefully through Noether's theorem and the FLRW metric and the comoving box and the equations of state of matter and radiation and gravity and dark energy and the cosmological constant problem and the zero-energy universe and the 3 honest positions and the local conservation that survives after all of that, we can answer the question that the title of this video asks. The answer is that the universe does not have to find energy anywhere to keep expanding because there is no rule that requires it to. The question carried a hidden premise. The premise was that energy is conserved at the cosmic scale. The premise is false. The conservation law that you learned in school is conditional on a property time translation invariance that our universe, at its largest scale, does not have. There is no global conservation of energy at the cosmic scale, because there is no global symmetry that would have required one. There is no debt. There is no creditor. The universe is not finding the energy to keep expanding. It does not need to find any. The accounting law that would have forced it to find some does not apply to the kind of universe we live in. Read that again, because it is the resolution. The accounting law that would have forced the universe to find energy somewhere to keep expanding does not apply. Not because the universe is breaking it, not because there is some loophole, not because some special process is exempt. The accounting law was always conditional. The condition was always specific. The condition was time translation invariance, and our universe does not satisfy that condition at the cosmic scale. The conservation law does not apply, and so the universe does not have to satisfy it. There is no creditor demanding payment for the new dark energy that fills every cubic meter of newly expanded space. There is no debt accumulating somewhere that has to be repaid. There is no rule. The rule did not exist. This is the resolution. It is, in one sense, a deflation. The question was malformed, and once you see the malformation, the question vanishes. There is no mystery about where the energy comes from. The expansion does not require energy in the way that the question implied it would. The dark energy density is just a property of the vacuum. The cosmological constant is just a constant in the equations of general relativity. The expansion is just what the metric does when the cosmological constant is positive. No transactions occur. No counterparties exist. The deepening of the puzzle was an artifact of bringing a flat spacetime intuition to a curved spacetime universe. But, in another sense, the resolution is not a deflation at all. Because once you let go of the original question, a new and larger question takes its place. The new question is not, where does the energy come from? The new question is, what kind of universe is the kind where the most famous law in physics is conditional? That is the question that this video sits with, and it does not have a tidy answer. It is a universe where the simple law of conservation of energy, the law that was taught to every chemistry student and every engineering student and every biology student for the better part of 2 centuries, is conditional on a symmetry that fails at the largest scale. That symmetry time translation invariance fails because the metric of spacetime is itself in motion. The structure of the universe is evolving. The rulebook is being rewritten as the calendar pages turn. The largest accounting system in physics quietly stops working at the scale of the universe, not because anyone is cheating, but because the metric is doing exactly what general relativity has been describing for over 100 years. It is a universe where 2 of our best theoretical frameworks, quantum field theory for the small, general relativity for the large, disagree about the energy of empty space by a factor of 10 to the 120th power, and we have not yet found the underlying theory that will reconcile them. It is a universe where the simple, beautiful, and incredibly useful local conservation of energy holds with extraordinary precision everywhere that you and I will ever observe, and where the global extension of that conservation does not exist. It is a universe where, when you ask, where does the universe find the energy to keep expanding, the cleanest answer a working physicist can give you is, it does not need to find any. That is the universe we live in. That is, the universe physics has been carefully describing for 100 years, and almost nobody outside of graduate school general relativity has ever heard the full story. You have heard it now. Walk back through the human stakes one more time. Every battery you have ever charged, every meal you have ever eaten, every joule of work your body has ever done, every chemical reaction in every cell of every living thing on Earth, every star burning, every photon emitted, every nuclear decay, every collision in every accelerator, all of it tracked perfectly under a bookkeeping system that was taught to you as universal. The bookkeeping system is real. The bookkeeping works to extraordinary precision, and the bookkeeping is local. Zoom out far enough past the laboratory, past the planet, past the solar system, past the galaxy, past the local group, past the supercluster, out to where the metric is visibly stretching, and the local bookkeeping does not sum into a global one. The global ledger does not exist. The largest accounting system in physics quietly stops working at the scale of the universe, and almost nobody outside graduate physics is told. The universe you live in is a universe where the rules of the box are changing as you try to count what is in the box. The phrase came up in part 3 when we first introduced the FLRW metric. We are returning to it now with a different feeling. In part 3, it was a problem. The rules of the box are changing, and so the bookkeeping inside the box does not work cleanly. In part 12, it is just a description. The rules of the box are changing, and so the global accounting does not exist, but the local accounting holds everywhere. And the local accounting is what every person who has ever done a chemistry experiment has been using, and the local accounting works. The thing that breaks the global conservation is the same thing that makes the universe interesting. The metric evolves, the scale factor grows, the cosmos expands, galaxies separate without moving, photons stretch and lose energy, dark energy fills the new space without source. The deepest mystery in modern physics, the cosmological constant problem, sits underneath all of it, unsolved. And the law of conservation of energy, the law that opened this video and that you were told was unconditional, turns out to be one of the most beautiful conditional laws in all of science. A lie to children. We named the phrase in part 1. We can name it again now, with the gentleness that comes from having walked through what the conditional version actually says. It was not a lie so much as an unannounced approximation, a sentence written for the part of the universe small enough for time translation symmetry to hold. The sentence is true everywhere you will ever do science. It just is not true at the scale of the cosmos, and the person who first taught you the sentence almost certainly believed it was unconditional, because they had been taught the same way. The full version sits in textbooks of general relativity. The full version sits in Noether's 1918 paper. The full version is what working cosmologists have been quietly using for decades. The full version was always there. It was just never said out loud where most of us could hear it. You have heard it now. There is no debt. There is no creditor. The universe does not need to find energy anywhere to keep expanding. The simple version of the law of conservation of energy was conditional all along, and the condition does not hold at the scale of the cosmos. The expansion is just what the metric does. Dark energy is just a property of vacuum. The cosmological constant problem sits underneath all of it, unsolved, the deepest open question in modern physics. The deeper question is the one we leave you with. What kind of universe is the kind where the most famous law in physics is conditional? What kind of universe is the kind where empty space has an energy density nobody can derive from first principles? The answer is not in this video, and it is not in any video because nobody has it yet. The answer will require a deeper theory of gravity, of vacuum energy, of how time itself emerges from the underlying structure of physics. Maybe quantum gravity will tell us. Maybe a holographic reformulation will. Maybe something nobody has thought of yet will. We do not know. What we know is this. The universe is not finding energy anywhere. The law that would have demanded it does not apply at the cosmic scale. The expansion is what the metric does. And the local conservation of energy that holds in every cell of your body, in every flame, in every star, in every photon, in every reaction, everywhere physics is actually done, is intact. It is real. It just does not extend to the cosmic scale, and at the cosmic scale, there is no extension to find. Sleep well. The universe is, as it always has been, stranger than the lie to children was ever going to capture, and the law was not wrong. It was just smaller than you were told. And smaller is still big enough to be one of the most beautiful and most useful laws in all of physics. The most famous law in physics has a hidden conditional. The conditional fails at the largest scale. The expansion is what the metric does. There is no debt and no creditor. The universe does not need to find the energy anywhere to keep expanding. It just keeps going, doing what the equations describe, while you and I sit inside it, in a small region where the local conservation holds exactly, watching the larger structure do what it does. That is the story. Thank you for staying with it.